In the name of God, the subject of our paper is about blind load balancing algorithm using double Q learning in the fog environment. Because of the dynamic of the fog environment, a variable number of mobile devices may be connected to each fog node at any moment. The fog node to which more mobile devices are connected receives more tasks than other fog nodes and will be overloaded. For this purpose, load balancing methods are used to evenly distribute tasks among fog nodes to avoid overload. The purpose of this paper is to present an optimal load balancing method for fog computing, for which we use the double Q learning algorithm. The result of this paper are as follows: reduce the average delay, reduce the standard deviation of the load on the nodes, improve load balancing operations, increase reward in the proposed method. The root of fog computing is the same as cloud computing. Both fog computing and cloud computing provide computing, storage, and networking services to end users, but fog is closer to the end user, thus providing minimal delay for IoT applications. In this paper, we consider a full layer architecture for the fog environment as follows. In the first layer are IoT devices that connect directly to fog nodes and send data to these nodes locally. The second layer is the fog layer. Fog servers can be located in different geographical locations and process data received from IoT devices in real time. The third layer comprises a proxy server that receives data from fog nodes and then sends this data to the cloud. The last layer in this structure is the cloud data center layer, which includes several servers and data centers. Because of this structure, data and information are processed locally at fog nodes, and there is no need to transfer data to the cloud. In the following, we will talk about the system model of the proposed method. We have formulated the proposed load balancing problem as Markov decision process to achieve the desired performance. The MDP comprises a decision-making agent that continuously observes the current status of the system, selects an action from the allowed actions in this state, and then transitions to a new state and receives a reward for that action, which influence future decisions. An MDP usually consists of SAPR, which are defined for proposed load balancing problem as follows. S is the state space that consists of 3 members, where n is the number of mobile devices connected to the fog node. C is the capacity of the fog node. Q is the forward queue size in the fog node. A is action space, where n represents the selection of fog node or cloud to assign the task. P is transition probability. R is the reward for select the action A in the correct state. The primary goal is to select the optimal action in each system so that the long-term value is maximized and the processing delay and overload probability are minimized. In the following, we will discuss how to calculate the reward and delay in the proposed model. The task processing time is equal to sum of the transmission delay and processing delay of that task in different devices, which is calculated as follows. In this formula, delta represents the transmission delay between 2 nodes that including 2 components. TW is the waiting delay in the forward queue of the source node, and TAS is the send delay on the communication channel between the 2 nodes. and data represent the processing delay of the task assigned to the fog node. In the proposed method, the double-Q learning algorithm runs on fog nodes in which we define the reward function as the negative of the processing delay. The longer the task processing delay as a result, the less reward is received. In this paper, R is calculated as follows. Theta is calculated in one of the following two ways. If the node itself that received the task from the mobile device process it, theta is calculated as follows, where TEI is the task execution time in FNI, but if the task is assigned to FNJ or the cloud for processing, theta is calculated as follows, where delta j is the task transmission delay from FNI to FNJ or cloud. TJ is the task execution time in FNJ or cloud. Delta j is the transmission delay, the result of the task from FNJ or cloud to FNI. The less the task processing delay as a result, the longer reward is received. After we have explained how to calculate the reward and delay in the proposed system, we will describe the proposed load balancing method below. In this paper, a double-Q learning-based load balancing algorithm for uniform load distribution among fog nodes is presented. The double-Q learning algorithm uses two estimation functions. This way, it used two Q tables for estimates that stored the value of all actions. The difference between the two tables is that when we update the value of one of the tables, we use the maximum value present in the other table. The double-Q learning algorithm uses the epsilon greedy policy to maximize a long-term value, in which epsilon indicates that the next action is randomly selected or that selected for among the best in the table. In general, the proposed algorithm works as follows. The mobile device assigns the processing of a task to the fog node. In this section, the double-Q learning algorithm is implemented. The fog node is considered as an agent and is busy learning in the network. After the fog node receives a new task via the mobile device, it observes the current state of the environment. Then, to maximize the long-term reward based on the experience and rewards it has received so far, and without any knowledge of the capacity of the other nodes and only according to its own capacity, it decides for the task processing. If the fog node has enough capacity, it processes the task itself. Otherwise, it assigns the task processing to the neighbor fog node or cloud. Finally, the neighboring node or cloud sends the results to the fog node. The fog node also sends the results to the mobile device. In the following, we evaluate the results. In this paper, we have used the ICCKE simulation environment to implement the proposed method. The proposed system includes n fog nodes and a variable number of mobile devices. Mobile devices randomly connect to their neighbor nodes and assigns processing their task to these nodes. In the simulation, it is assumed the mobile devices now send tasks to fog nodes and the double-Q learning algorithm is executed simultaneously with received task by fog node. This will prevent overload in the nodes as much as possible. However, in other methods, unlike the proposed method, the load balancing algorithm is executed after creating an overload in the fog node. This leads to reduced performance and increases the delay in these systems. In this paper, the reward is equal to the negative of the processing delay of the task assigned to the fork node, given that each task is processed by which node increasing the processing delay of a task reduces the reward received for processing that task. As shown in the figure, the assigned decision of the task based on the double Q learning algorithm with the suitable distribution of tasks between nodes has gradually increased the cumulative reward. And then we've seen that as the reward increases, the average delay is reduced. The average delay decreases if each node learns to assign task processing to a node with more capacity. As a result, it can process the task faster. As you've seen in the figure, with increasing learning, the standard deviation of the load on the nodes decreases. In this paper, the performance of double-Q learning load balancing method is compared with SSLB, proportional, and random load balancing methods. In the random method, a node offloads tasks to a randomly picked neighboring. In the proportional method, the capacity information of the neighbors is received and selects the optimal one to offload a task. In the SSLB method, after a fog node is overloaded, it compares the capacity of the other neighbor nodes and sends the task to the node that has at least 30% of its capacity in PT and has the highest capacity. In the following, we see the results of comparing these four methods. As shown in this figure, the assignment of tasks based on the double-Q learning algorithm with the proper distribution of tasks among fog nodes has enabled the nodes to process the task faster, and as can be seen, the average delay in the proposed method than compared methods has improved dramatically. Finally, the standard deviation of the load on the nodes is compared in all four methods. According to this figure, at first in the SSLB method, the standard deviation of load on nodes is less than other methods. However, with increasing agent learning, the standard deviation of the load on the nodes is the proposed method is significantly reduced. This indicates that in the proposed method, the tasks are evenly distributed in the network, and the possibility of overload and underload in the nodes is reduced. Finally, we present a conclusion from their work. The proposed load balancing algorithm is compatible with the distributed nature and the dynamics of the fog computing. Processing delay and user response time are improved. Find low load fog node to assign tasks, avoid overload and low load of nodes, and improve load balancing. Thanks for your attention.